This is the first 10.2 video, and in this video, we're going to describe the shape, center, and spread of the sampling distribution of a difference between two means, and we're going to determine if the conditions are met for doing inference about a difference between two means. So, do freshmen or seniors spend more time on their phones? The growing popularity of smartphones, high school students spend more time on their phones than they did in the past. Ms. Barbero wonders if there is a difference between the amount of time freshmen spend on their phones and seniors spend on their phones at her high school. She takes a simple random sample of 50 seniors and a simple random sample of 60 freshmen and records the average daily screen time for both samples. The 50 seniors had an average daily time of 9.25 hours, and the freshmen had an average daily screen time of 8.5 hours. So essentially what we're doing here is we want to see if there's a difference between two populations. And the two populations are the freshmen at Ms. Barbero's school and the seniors at Ms. Barbero's school. And in order to do our methods of inference, so create a confidence interval for the difference between these two means, or a test about the difference between these two means, we have to understand the sampling distribution of the difference between two means. And so that's what I'm going to teach you in this process. And I want you to think about, from the two populations, what would the sampling distributions look like? So you have to remember, a sampling distribution is if we take all possible samples from a population. For instance, if we took all possible samples of size 50 from the seniors and we plotted the average screen time from each sample over and over again, what would the shape look like? Well, we've done this before. We know it's going to be approximately normal because the sample size is 50. Central limit theorem says if it's 30 or more, then the sampling distribution will be approximately normal. So let's draw out what these sampling distributions would look like, and then we'll go on from here. Here is what we can expect the sampling distributions from both populations to look like. Since the sample size of the seniors was 50, that means it's greater than 30. So the central limit theorem applies. It'll be approximately normal. And it will be centered at whatever the true average amount of time seniors spend on their phone is. And so let's just assume, since the average was 9.25 for seniors, let's just assume we actually do know that the population mean was 9. So then this distribution, it would be centered at 9. And we got one sample that was 9.25, so maybe that's this sample up here. And I just wrote a couple X bars as a reminder. This is all possible samples taken from seniors. So if it's centered at 9, then the mean of this distribution will also be centered at 9, and the standard deviation of this distribution is going to be whatever the population standard deviation is, sigma, divided by the square root of the sample size, which would be the population standard deviation divided by the square root of 50. Now, the same thing will be true for the sampling distribution from freshmen. Again, we're plotting all possible sample means from all possible samples of freshmen at the school, and it will be approximately normal because the sample size is 60, greater than 30. It'll be centered at whatever the population mean is. In this case, let's just pretend we know that it's centered at 8. So if the true average amount of time freshmen spend is 8, then the sampling distribution will be centered at 8, and the spread of the sampling distribution will be whatever the population standard deviation is divided by the square root of the sample size. So we've talked about these before and you understand these, but what we're going to have to use for two sample t intervals and two sample t tests is the difference between these two sampling distributions. So what we're going to be curious about is what's the average distance between these two, or the average difference between these two, and what variation will that distribution look like? This third sampling distribution, the difference between the mean of the seniors and the mean of the freshmen, is the one that we're going to use for inference about the difference between two means. So essentially what this sampling distribution is that I'll draw down here in a second is if we take all samples from seniors and subtract from that all samples from freshmen. If we repeat that over and over again, for example, like our sample that we had here from Ms. Barbero was 9.25. So that's maybe this sample here. And the sample that we had from the freshman was 8.5. So that's maybe right here. If we subtracted this value from this value and plotted the difference over here for all possible samples, that's what this sampling distribution is describing. And so I'm going to draw out what we know the shape, center, and spread of this distribution will look like. I've drawn two examples like I discussed earlier, where we take a sample of seniors and subtract the sample from freshmen, and we plot that value there. If we did that over and over again, we would expect it to be centered at the true difference between these two populations, which would be 9 minus 8. So the mean would be centered here at 1. The standard deviation is going to be the combination of these two variances. So remember, since we're taking two distributions and combining them, we're going to have a more spread out distribution here. That is the combination of these two variances. So if this is the standard deviation, we're going to add their variances together. I would have to square this value and add it to this value squared. So this is what it would look like. This here is what the standard deviation of this distribution would look like, because this square would give us sigma squared over 50, and then we add them together and take the square root to get the next standard deviation. So really, this tells us that this sampling distribution will be centered at 1 with a standard deviation of whatever this would end up being. And we can only know that if we know the population standard deviations, which is very unlikely. And we also know that this will be approximately normal because this sampling distribution is approximately normal and this sampling distribution is approximately normal. So if both of them are approximately normal, then the difference between the two will also be approximately normal. This third distribution is going to be the sampling distribution that we use to conduct inference about population means when we're comparing two groups. The only issue is right now, to describe this distribution, we assumed that we knew the mean of the seniors and the mean of the freshmen, and we don't know what the population standard deviations are. And whenever we're conducting inference, generally, we don't know what the population means are or the population standard deviations are. So instead, we're going to substitute these sigma values here for S, our sample standard deviation, and it's going to be called the standard error of the sampling distribution. So I'm going to write out the formula for our confidence interval if we were trying to create a confidence interval for a difference between two means here. The simplest form is you're taking your point estimate plus or minus your margin of error. Now, in this case, our point estimate, if we're trying to estimate the difference between two population means, then our point estimate is going to be the difference between our two sample means. The margin of error is composed of two things: the critical value and the standard error. So the critical value, if you remember, is going to be a t critical value, because whenever we have a sampling distribution of means, it has more area in the tail, so we use the t distribution instead of the z distribution. You should also remember that the t value is dependent on the degrees of freedom, and your degrees of freedom is whatever your sample size is minus 1. So in this case, if we have two samples, what we're going to do is we're going to pick the smaller of the two samples and use that as our degrees of freedom. So our degrees of freedom for this problem would be 50 minus 1, 49 degrees of freedom. The standard error is going to be this formula here, but now we're substituting in whatever our sample standard deviation is, because it's very unlikely that we know sigma. This here is the basic formula for a confidence interval for a difference between two means. Now you might see this written as the standard error of x bar 1 minus x bar 2, look like this. So the symbol you might see is SE, the standard error of the difference between these two. Now, before we can actually use this formula, we have to make sure that we have an approximately normal distribution, and we have to make sure we have trustworthy samples. So that's where the conditions come into check. The first condition, we have to make sure that both samples were random and they're independent, or they come from a randomized experiment. Next, we have to check the 10% condition. The samples have to be less than 10% of the total populations from freshmen and seniors. And then finally, we have to make sure these sampling distributions are approximately normal, meaning this one will be as well. And the way we check that is the large normal. So if our sample is greater than 30, we're good to go. If it's not, we can still look at the sample and make sure there's no strong skewness or outliers like we've done in the past. Also, if the sample size is less than 30, we can still proceed as long as the population is approximately normal. So let's take a look at an example problem for actually creating a confidence interval for a difference between means.